Hello everyone, this is Rhyan Klima, and today we're going to look at a combined spectral problem, specifically looking at C6H12O2. As you can imagine, with a combined spectral problem, there is a lot to unpack here, so we're going to approach it with a step-by-step process. First, starting with carbon-13 nuclear magnetic resonance spectra, then we are going to go to infrared spectra, then we are going to go to hydrogen-1 nuclear magnetic resonance spectrum, and finally putting all that information we discuss into our tables here with the outcome of looking at building a correct proposed structure. Now, some other things that I found helpful were these charts of chemical shifts and spectra that was found in our reading and our homework, as well as I just like to keep our periodic table of elements on hand, especially when looking at electronegativities of atoms. Now let's get started. All right, starting out here with our first step with our carbon-13 nuclear magnetic resonance, looking at the carbons. So outright, we can see we have a scale from 0 to 200 parts per million, and we can see 6 peaks here. 1, 2, 3, 4, and then there is actually 2 over here, 5, and 6. Even though they almost look like they're one, there are 2 distinct peaks. It's very subtle, but it is definitely there. So that gives us an indication that we're looking at 6 unique carbons throughout our structure, making our structure potentially very diverse. The next thing we're going to look at here is we're going to circle this 80 parts per million. This is a particularly interesting barrier, as one might want to call it. On this side, so we're going to draw here, this area is kind of considered more upfield. This is going to be where you find your sp3 orbitals, resulting in your tetrahedral geometry. And then to the left here is what's considered your more downfield region, which is going to have your sp2 orbitals, which results in your trigonal planar geometry. Now there's 2 peaks I want to focus in on here. First, our second peak at about 60. This is most likely our carbon to oxygen singular bond, as it is very common for these bonds to show up at the 50 to 80 parts per million range. And then this peak, our first peak here, this is going to be our carbon to oxygen carbonyl or double bond. One can tell this based on their previous knowledge of the spectral data in terms of electronegative atoms, which is going to be our oxygen here and our oxygen here, are most greatly affected by the magnetic field. So with the carbon to oxygen single bond, it's still in the upfield region, but it's going to shift downfield because of the pull of the magnetic field in the oxygen. And our carbon to oxygen double bond is going to be way down here in the higher parts per million range, very downfield, again to that very electronegative pull downfield. Okay, so now we're going to look at our infrared spectroscopy. As you can see, I have a couple functional groups here written out, but we'll get back to that. I really enjoy the infrared spectroscopy because it provides so much information. So we're just going to kind of start here, looking at this extreme peak that dips around down to about the 1700, and this is an indication of the carbon to oxygen double bond stretch here. And then we'll come over here and jump over to this kind of other long peak at 1150. This is indicatory of a carbon to oxygen single bond connection here, and this is also a stretch. And then we kind of notice this peak here that's just below that 1500 line, and that is going to be indicatory of your hydrogen, carbon, hydrogen bending. And then looking at the hydrogen and carbon as well, we have the hydrogen carbon peak here that indicates a stretch. Now this kind of area over here where it gets a little bit more complex, this is considered the fingerprint region being that it is unique to the molecule. Now there is some debate whether that line starts kind of directly at the 1500 or is it more closely to the 1300 or the 1200 mark, but it's kind of this general area. Kind of above that is considered the group frequency area. Now to kind of come over to these functional groups here that we can start to look at. So from our information that we are starting to gather, we have the carbonyl, which makes sense. We kind of talked about that up here, as well as the carbon to oxygen single bond, which is what we also talked about up here. So we can start crossing some things off by what peaks we see and what kind of absences we have. For example, we can cross off the carboxylic acid because there is no indication of a large rounded alcohol group of here. And kind of looking in that same area, we can also cross off the amide because we don't see a little double peak or double bump amide over in that region, kind of closer to the 3300 area. So the aldehyde is a little bit more difficult, but we're also actually going to be able to cross that one off, and that is because the aldehyde shows a kind of double peak here with that kind of between the 2750 to 2850 range, and we're not seeing a prominent second peak. It's kind of just sitting that between that 2900 and 3000 mark, so we can actually cross that off. And then we're left with the ketone and the ester, and from our information that we're kind of already gathering that we also have a carbon to oxygen single bond, we're going to go ahead and cross off the ketone and go ahead and circle that ester. Now to look at our final spectra here, we are now on hydrogen 1 nuclear magnetic resonance. To start out here, we have our scale 0 to 11 parts per million, which is comparatively a lot less than your 0 to 200 on your carbon-13 nuclear magnetic resonance spectra. So we're going to look here. We have a lot of data. First, we have 5 clusters. We have 1, 2, 3, 4, 5, which gives us a further indication of 5 signals, or the indicating of 5 unique positions. We kind of saw that with the carbon magnetic nuclear resonance spectra as well. Then looking at the integral data, so which is the numbers and letters kind of above here. This is what's considered the normalized version of the integral data. Looks like we have 2 hydrogens in this unique position, 2 hydrogens in this unique position, and so on and so forth, saying 2 hydrogens here, 3 hydrogens there, 3 hydrogens there. Now we're going to look at the peaks, or the multiplicity of each hydrogen cluster. So if we count here, we got 1, 2, 3, 4. 4 peaks in that cluster. We have 1, 2, 3 in this cluster. 1, 2, 3, 4, 5, 6 in this one. 1, 2, 3 in this one. 1, 2, 3 in this one. So what that means for us, we have a quartet here. We have a triplet here, a sextet here, another triplet here, and another triplet here for coupling names here. Now, considering the neighboring kind of rule, it is 1 less than the number presented here, so that means there are 3 neighboring hydrogens nearby, 2 neighboring hydrogens nearby, 5 neighboring hydrogens nearby, and then 2 again for neighboring hydrogens nearby. Now there's 2 other things to indicate here. With this sextet and this 5 neighboring hydrogens nearby, it looks like it is a splitting. It's coupling, meaning it's in between 2 other carbons with hydrogens on them nearby, so meaning there's 1 on either side. And then the other one to look at here is this is quite high in the chemical shift here, moving down towards the downfield portion of the graph, and this is an indication of a hydrogen bonded to an oxygen. Again, kind of same concept from the carbon, nuclear magnetic resonance, that the magnetic field affects the electronegative atom, which is your oxygen, causing it to shift in your spectra here. Okay, so now that we've finished looking at our spectral data on a visual level, now we're going to be able to pull that information and put it in some tables to help us achieve the ultimate goal of building that proposed structure. So we have here our molecular formula, the C6H12O2. We're going to go through the degrees of unsaturation here. So starting with our formula, again, C6H12O2. We actually don't care about oxygen in this, so we're going to only look at the carbon and the hydrogen. Now we have this formula, the 2N plus 2. It's going to help us find the saturation that should be. So we have 2 times number of carbons, which is 6 plus 2. That is going to result in here with a 14. So to have full saturation, we're actually wanting to have a C6H14. So what does that mean for us? We're going to look at another formula that has the expected number of hydrogens, which we determined is 14, minus the observed number of hydrogens, which is that 12, and that's going to give us our 2 here, and that degree of saturation is going to be half that number, which is 1. So ultimately, we have 1 degree of saturation, which indicates that we have only 1 double bond, which makes sense because from our other data, we have concluded that we've seen a carbon to oxygen presence in the spectral data, so that kind of follows along with what we've already been surmising here. Now, to follow with the rest of our data, this is the table from infrared spectroscopy. We just pulled the numbers that we were observing, those peaks, and discussing there. Our functional groups, again, we talked about it a little bit. The carbon to oxygen single bond, the carbon to oxygen double bond. You have and then the hydrogen, carbon, hydrogen. and the carbon hydrogen, and just the same thing that we talked about: stretch here, bending here, stretching here, identifying an ether here and an ester here. Moving down into the carbon-13 nuclear magnetic resonance, we just pulled the parts per million that we were looking at the peaks on the spectral depiction, and then just giving some more information about the type of bonding environment. So here we'll go ahead and we'll highlight the carbons that we are talking about. So here, the chemical shift for 173, we're going to talk about this carbon and the carbonyl. For 60 parts per million, we're looking at the carbon attached to the heteroatom, which is the oxygen. Here we're looking at the carbon attached to the carbonyl, which is this one. Here we're looking at a 2-degree carbon, which means it's attached to 2 other carbons, putting it in the middle. And then the last 2 are both 1-degree carbons, indicating that they are only attached to one of the other carbons. So we have here at CH3 and CH3. And then finally, kind of following up with our hydrogen nuclear magnetic resonance, just again, those parts per million with the relation of the integral data, and we talked about the multiplicity that we pulled already, and then just kind of the interpretation, which we already kind of talked about. So quartet, meaning there are 3 neighboring hydrogens, and then so on and so forth. We determined that this one in particular at 4.2 is going to be attached to your oxygen, and then here at 1.7 we have 5 neighboring hydrogens, which is going to mean it's split coupling, which means there's going to be a carbon on either side with hydrogens on each side. Okay, so we are at our final step where we're putting together a proposed structure, and I'm just going to go through my thought process here, starting with the carbonyl, which we ascertained from the carbon-13 nuclear magnetic resonance that is 173 parts per million. And then we also discovered through a couple of spectral depictions that it does have an ester, so I threw that ester in here. Now moving over to this carbon, from the hydrogen-1 nuclear magnetic resonance, we figured out that this is about 4.2 parts per million, indicating that it is most likely whatever carbon this hydrogen is attached to is most likely attached to the oxygen because it has a higher parts per million indication. And this also, we know that this one is also indicated as a triplet, which means there are 2 neighboring hydrogens. So jumping over here, there's our 2 neighboring hydrogens. And this one is going to be our 1.7 parts per million. And this one indicated that it was a sextet or a multiplet, meaning it has neighboring hydrogens on both ends. Sextet meaning there are 5 neighboring hydrogens, so we have 2 over here and 3 over here. So that pans out, and that makes a lot of sense. And then moving farthest over here to this methyl group is going to be our 0.9 parts per million. And this one indicates it is also a triplet, so it indicates that there are 2 hydrogens nearby, which looking to the left, there are. So coming over to this CH2 group over here, this is a 2.4 parts per million. It is still kind of high because even though it's not attached to an oxygen, it is nearby the carbonyl. So we have 2.4 parts per million, and this one is a quartet, meaning that there are 3 hydrogens nearby, which makes sense if we look to the left. There's our 3 hydrogens with our last and final methyl group coming in at 1.3 parts per million. And this one is a triplet, indicating there are 2 hydrogens nearby, which is these 2 right here. The reason why we know that this methyl group is on this location and not over here is because this methyl group has a 0.9 parts per million, meaning it is farther away from, let's call it, all of the action. So all the action is going down here. It has a lower parts per million, shifting more upfield. And down here, this is only removed one other carbon over, where this is removed a couple. So that's going to be our slightly higher parts per million at 1.3. So that is all today. Thank you for staying with me through the spectral depictions, as well as following along with our tables and our degrees of unsaturation and our proposed structure.